Welcome everyone to the Ontology Summit 2021. I am very pleased to introduce our speaker for today, John Sowa, who has been a regular contributor to the summit and is a member of the Board of Trustees of the Ontolog Forum and has been part of the organizing committee for the summit. And today he's going to be speaking on automated and semi-automated methods for deriving ontologies. Go ahead, John.
Okay, now this diagram in the middle, this hexagon, shows that all of the things that we're doing relate in one way or another to language. So our native languages and the languages we learn are the most important languages we use for communication, and they're far more natural for us to think in and to talk in and to work in than any artificial language of any kind, including all our programming languages and versions of logic and all of them. And so if we want to develop our ontologies, we have to develop them in such a way that they have a smooth mapping to and from our natural languages. And this diagram in the middle shows how language is related to all of the related parts. Now, I have quite a few slides, and I'm not going to be able to go through all of them in detail, but I want everybody to have a copy of them because they will, the more details there they can read at their leisure to get some more details. So the basic point that I want to start with is that the semantic web is obsolete. The technologies developed for the semantic web are at least 20 years old. Some of them are 30, 40, 50 years old. And there's a lot more that has been done since then that isn't being represented. And there's a lot more new developments in the past 20, 30 years that are very important. So I first want to start with talking about the semantic web and why it's obsolete. The second point, I want to talk about interoperability among heterogeneous systems, which include the legacy systems, which still run the world economy. So all of these new things that are based on formal ontologies are just special cases. And I'll talk about common logic as the semantic web logic language, as Tim Berners-Lee had intended. Then I'll talk about mapping logic to and from natural languages. Then I'll talk about cognitive memory and automated and semi-automated tools. So there's a lot of things that I'll talk about, and I won't be able to spend much time on any single slide. Now, the first thing, the next slide 3 is talks about the semantic web. Let's see, see my screen. Can I get some of these, minimize some of these other things that are covering this? Can you see the whole screen? Because there's also, Zoom keeps putting all these other things in the middle on the side.
We see it, John.
Fine.
Okay, you see it fine, because I see stuff hanging around on the sides, which are a nuisance. Okay, the point is that Tim Berners-Lee wrote a very ambitious proposal of which only a small part was implemented. And the goal that I'm proposing is to implement Tim's original vision with a new generation of tools with more advanced methods for language, learning, and reasoning, and better methods for building trust and ensuring security. And the next slide shows the layer cakes as they developed. The one on the left was the DAML requirements by Jim Hendler. And he had a lot of things at the top. Notice there's higher order logics, fuzzy logics, and operations that don't appear in any of the current technology sanctioned by the semantic webbers. In the middle is the winning proposal that Tim proposed. And notice that big double arrow, the yellow arrow, that is the semantic web logic language that is used for communication among all of them. And common logic, which was developed by Pat Hayes and Guha, they developed the foundation for that and according to the specifications that Tim originally specified. And the final report had logic shrunk to this tiny little piece, as opposed to the Tim's original vision, in which logic was a big double arrow. And I think that is a serious limitation of what happened to the semantic web. And for a couple of examples, I mentioned that there's a new work that's being done on knowledge graphs, and the term knowledge graph came from what Google had been doing, in which they had used a wide variety of resources, the DBpedia, Wikipedia, and the most advanced AI methods that they had available. For the Jeopardy challenge, IBM also used DBpedia and Wikipedia, but they had even a much wider range of AI technology. English parsers, question classification, question decomposition, automatic source acquisition, entity and relation detection, logical forms, statistics, machine learning, knowledge representation, and several methods of reasoning. They had a huge amount of work that goes far and away beyond the semantic web. Now, this work was done 10 or 20 years ago. And today, the work that was done by these multi-billion-dollar corporations is technology that we can now run on our laptops. And that's the point, that the automated and semi-automated tools should be able to use the same kind of technology that the big boys were using 20 years ago, and now running on our laptops. Now, the next slide shows that hexagon again, and it shows that every part of the hexagon represents some action, some aspect of our thinking and reasoning. At the top is the diamond crystal that represents ontology. At the bottom is the world with all its huge amount of complexity. And then in the middle is language, which relates on the left corner. There's the symbolic models, which can be represented as graphs or RDF or many different kinds of notations and logic. And on the right is the reasoning. There's the thinker who is thinking about the ontology and its relation to action and language. And at the lower left corner is a mental model in which we see somebody thinking a mental model of a cat on a mat, which can be mapped to and from your symbolic model, to and from your language and the world. And on the lower right, there's an action figure of a jockey on a horse racing. And all of these things are related to one another, but the central relationship is through our good old-fashioned natural languages. And that is the form that everybody is using. Now, everybody on the screen who's listening into this knows something about ontologies and programming languages and ways of using ontologies for knowledge representation. But yet, when we're talking and writing, we all communicate via our favorite language or whatever we have learned to use. And so the point is, the corners of the hexagon represent aspects of knowledge, and natural languages represent conscious knowledge. But in addition, we have a huge amount of unconscious knowledge about the way our body works and the way our body connects to all the tools that we're using when we're driving a car. The car is in effect an extension of our body, and we feel the way our extended body is moving as we drive. And all of that must be represented in some way or another if we're in the tools that we use to reason. And so the challenge at the bottom is to implement AI tools that can support all of the above. Now, one tool that I want to mention is DOL, D-O-L, and that is the Distributed Ontology Modeling and Specification Language, which has been standardized by the Object Management Group. And at the bottom is a link to it. And I believe that this standard is very important. I think this is far more important than the ISO standard for top-level ontologies. Doug Lennett, from the Psych developer, said that the top level of the ontology is the least important part. And I totally agree with him that the top level of the ontology is not something that we should be emphasized, because all of the real work is done in the middle levels and the lower levels. At the top level is important to organize things. It's basically an organization method, but it's not really fundamental for reasoning. Now, one thing about DOL is that they have been representing not only the semantic web logics, but also formal UML, and that's also another standard of the OMG. And the point is that the DOL can relate multiple logics and multiple notations. And in the picture there shows many different diagrams from the UML diagrams. And the important thing is that if we want to share data among multiple computers and multiple people and multiple legacy systems, UML has been around for a lot longer than the semantic web. And there's a lot of usage of those diagrams for communication and representation of legacy systems. And we want to be able to represent those as well as any kind of logics in the semantic web. Okay. And there's another collection of the usage scenarios for DOL, and the bottom at the very top there's a programmer's lament who happens to be Terry Rankin, who also subscribes to the Ontolog forum, and this was a comment that he made at a database symposium about back in around 1980, and I still remember that, and I quote him all the time because he made the most important comment that anyone can make about all the available tools for software development. Any one of those tools by itself is a tremendous aid to productivity, but any two of them together will kill you. And that is the problem with all these tools for software development. If you start using one of them, you get sucked into it and you can't escape. It's like the Microsoft Roach Motel that you can check in, but you can't check out. And the problem is that these tools are every one of them has its own peculiarities and they don't communicate among them. What we need is methods for interoperability among all of the different methods and interoperability with all the methods for expressing the stuff in natural languages. And one point is the SWEL, that's the semantic web logic language that Tim Berners-Lee proposed. And Common Logic was the version of logic that was designed to support it. And one of the dialects of Common Logic is called CLIP. It's the CL interface to predicate calculus, which is a linear dialect of Common Logic that has a simple mapping to and from graph logic. The point is that Common Logic is the logic that was designed to be represent Tim Berners-Lee's version of SWEL. And here's an example of various logics. Gottlob Frege had the first version of first order logic, and that's the way he said a cat is on a mat. And if you read that, it says, I assert that it is false that for every x, for every y, if x is a cat, then if y is a mat, then it's false that x is on y. Now that is not a good way to say a cat is on a mat. And although Frege was first, no one else had ever adopted his notation. Now Peirce invented the algebraic notation for first order logic in 1885, and that looks very similar to our modern notation. Giuseppe Peano changed the symbols. He used backwards E's and backward E for there exists an X, there exists a Y, X is a cat, and X is on Y, and Y is a mat. Now, 1897 is when Peirce invented existential graphs, and there's the way he says a cat is on a mat. And you can't get any better than that. The lines represent an existential quantifier. There exists an X, which is a cat, and it's on a Y, which is a mat. And conceptual graphs are a notation I developed in 1976, which is based on an extension of Peirce's notation. It says there exists a cat on a mat. And then CLIP is the dialect which says there exists an XY, X is a cat, on XY, and Y is a mat. And here's the summary of the existential graph notation. One page, that's all you need to have the basic summary, and a short little 5-page summary would give you the entire syntax and semantics of existential graphs. Very simple. A line represents there exists. An oval, a shaded oval, represents not. And then relations have one or more links to them. They're represented by words or other symbols with one or more links. And there's a cat is on a mat. Something is under a mat. And this is there exists a cat which is not on a mat. Some cat is not on a mat. there's a cat which exists outside, and the line begins on the plain white sheet outside. And then in the negated part, it says that that cat is not on some mat. And then if you want to say some cat is on something that is not a mat, you just move the shaded oval to negate just the mat. And if you have a nest of two negations, then you have an if-then statement. If a cat is on a mat, then it is a happy pet. That you now know the basic syntax of existential graphs. In one slide, there's your summary. Now, clip notation is also a one-slide summary, and it has exactly the same examples, except that it's all a linear form. So this clip is a linearized notation for an open-ended variety of diagrams. You can take most, if not all, of the diagrams of UML and map them into clip. And all the logics of the semantic web, anything you can express in common logic, you can represent in clip. And clip notation has a one-to-one mapping to existential graphs and to conceptual graphs and to many, many other kinds of graph notations. Now, the point is that clip can relate legacy systems to the latest AI tools. You can mix and match any notation supported by Dole. Anyone may continue to use their favorite notations indefinitely, and all the semantic web annotations may be replaced by clip. But the point is you don't have to replace them. If you want to use OWL forever, you can do it because the Dole provides the technology for relating one notation to another. So if you want to stay with the old-fashioned notations, by all means, you can stay with them forever. And if you want to move to a new one, you can move to a new one, and the system will freely let you mix and match them as you wish, because all of the notations are related to one another by means of common logic, so that the old notations never become obsolete, because they're all subsets of common logic, and they can always map to your new version. Now, relating logic to natural languages, this is an area where there's been a huge amount of research for years. And one popular notation that people have been using is the DRT, which is the pardon? Oh, sorry. Okay, the discourse representation theory by Hans Kamp. And the notation that he had is discourse representation structure. And Hans Kamp's DRS is exactly equivalent to the subset, the basic first order subset of existential graphs. And on the left, there's one of Kamp's examples. If a farmer owns a donkey, then he beats it. And there it shows on the left is an existential graph that says it is false that there exists a farmer who owns a donkey and that he does not beat it. Or you can also read that if a farmer owns a donkey, then he beats it. That's the representation for if then. And the DRS notation is exactly equivalent. It says if there exists an X and a Y, farmer X owns XY and donkey Y, then X beats Y. And both of the existential graph and the DRS notation map to exactly the same clip. That means you can mix and match them freely anytime you want to. And as a matter of fact, there is free software. The Attempto Controlled English, ACE, translates a version of controlled English to DRS notation. And once you're in DRS notation, you can go via clip to existential graphs and to anything that is represented in the semantic web or in formal UML and other kinds of things. Here's another example of disjunction. That's the either or representation. And this is an example by Kamp and Riley from their book. Either Jones owns a book on semantics, or Smith owns a book on logic, or Cooper owns a book on unicorns. And there is an example of the existential graph, which has outside of the oval, it has Jones, Smith, and Cooper. And then there are three lines that go into the inside. And in this, there are the three alternatives. It says either Jones owns a book on semantics, or Smith owns a book on logic, or Cooper owns a book on unicorns. And then in the middle is the DRS notation, which is an exact one-for-one mapping to and from the existential graphs. And then at the bottom is the clip notation, exact one-for-one mapping of there. And so the point is that it doesn't matter which notation you prefer. You can map them all one to another. And if you want other notations in the semantic web, you can use clip to map it to them. If you want other kinds of diagrams, you can map them to and from existential graphs. The point is you have a universal form for relating anything to everything. And here's conceptual graphs. Now, conceptual graphs go beyond existential graphs by adding more features. So they add, for example, there it says that if a farmer owns a donkey, then he beats it, but it has the yellow things are the relations of thematic roles. They call them thematic roles or case roles. There's the experiencer. A farmer is experiencer of owning. The theme of it, owning, is a donkey. And if a farmer owns a donkey, then the farmer is the agent of beating the donkey. And there you have all those examples. And there is a footnotes all the way through where you can find references if you want to go into more detail on any of these things. Peirce also talked about meta language, and here's an example of an existential graph. It says that you are a good girl is much to be wished. Now, he used a shaded oval for negation, but if you just have a plain oval with a line attached to it, this means there exists a proposition that you are a good girl, and that proposition is much to be wished. And you can map that into a clip notation, is much to be wished, bracket, you are a good girl. There's no negation in front of it, so it's just that you wish that proposition. Let's see, what happened here?
I think it went out of memory.
Let me see, that should not happen. Okay, well, let me restart. Okay. Oh, somehow here it is back again. Well, okay. Meta language and clip. This shows more examples of, where's that? Oh, there was a diagram here. It was a very nice diagram. Oh, well, I'll skip the diagram. You'll be able to look at the details. I'll just skip that diagram. It talks about meta language and clip. And here is some more meta language represented in conceptual graphs. And you can download those slides and read them yourself. What is going on here? Okay, the next is cognitive memory. Now, one of the things that I want to talk about is automated mapping to and from your various kinds of natural language and programming languages into formal logic and other notations. And this is a project that is 20 years old. This is a project that Aaron Majumdar and Andre Leclerc did at the end of November of 2000, November of 2000, that just over 20 years ago. And this is an application that is absolutely amazing, that they developed, that Aaron had developed cognitive memory as a system for processing conceptual graphs and using them to store large volumes of graphs and to refine them in logarithmic time and use them for both pattern matching in ordinary language, in translating natural languages to logic, in translating programming languages to logic. And the programming languages he used at first were COBOL and the IBM Job Control Language, JCL. And he had a fantastic application, which is still the state of the art, or beyond the state of the art. I have never seen anybody do this same kind of thing to the level that Aaron and Andre did back in November of 1920. And it's based on cognitive memory, which is a system for mapping graphs to and from an internal notation that gives you a high-speed associative memory for graphs of any kind. And you can read the slides yourself to get more detail. And the point is that the cognitive memory preserves the exact structure of a graph. It's a lossless encoding of similar to a Gödel numbering. And it's far more, it preserves all of the information. And if you may have heard of word vectors, which are sort of a simpler kind of notation, and they're based on a kind of a bag of words that ignores the connectivity. The word vectors are useful for measuring similarity of texts, but they discard all of the structural information that's necessary for reasoning, question answering, and language understanding. The point is that cognitive memory is 20 years ago was an outstanding program that still today is beyond the state of the art. However, what Aaron will talk about as soon as I finish, he's going to go into the latest version called graph stacks, and he'll talk about that, which goes beyond what cognitive memory did to have stacks of multiple graphs that can be related to one another and to anything. And so it does it's sort of like a super cognitive memory that's much more general. And Aaron will talk about that. Okay, now the point is that we want to have something that will do perception as well as cognition. Deep neural networks are designed for perceptual learning. They're basically the kind of learning that you do when you learn to recognize faces, recognize scenes, recognize people, recognize all kinds of things. But they take a huge amount of training and a huge amount of data to learn the patterns. The traditional AI tools were designed for cognition. There you had parsers, translators for natural languages, grammars, lexicons, ontologies, inference engines, rule-based systems, formal logics. And some people have claimed that there's this competition between them. But the point is, humans do both. Humans learn language, and they learn to do cognitive reasoning as well as pattern recognition. They learn the pattern recognition from looking out in the world. And what we need are systems that combine both. You want to have a cognitive memory, which does learning and reasoning for cognition, and combine that with the neural network so that you have a complete coverage of everything. And that's one of the reasons for going to the graph stacks, because it gives you a better integration of the representations for everything in a common system. Now, the point is that common logic, cognitive memory can do both exact matching and approximate matching, and that is very important. And I'll talk about this application. This was a project for a company called Towers Perrin. We haven't talked about it for some time because we're talking about their proprietary systems. But the thing is that we're now talking that Towers Perrin has now been absorbed by other companies, so it's merged in with a lot of other companies. And this was 20 years ago, so we're going to talk about this stuff, and I'm going to mention how this thing works. I'll skip over this example because I don't have time to describe that, but I want to talk about the application to legacy reengineering. This is the one where Aaron and Andre did a fantastic job. This was a company, Towers Perrin, which had programs in daily use, some of which were up to 40 years old. 1.5 million lines of COBOL programs, several hundred scripts in JCL, the IBM job control language, 100 megabytes of English documentation, reports, manuals, email notes, Lotus notes, HTML, and program comments. Now, that's a small amount by today's standards, but it's still a huge amount of work. And what the company wanted to do, they wanted to do a complete re-engineering of their software, and they went to a particular one of these little small consulting firms. It used to be called Anderson Computing, but they changed their name to they changed their name to Accenture. And Accenture said that doing this job would take it would take something like the total amount of time, I forget what it would take 40 people 2 years with 40 people, or 20 people 2 years. Anyway, it was 40 person years of human work to do all the analysis. The goal was to analyze the COBOL programs, analyze the English documentation, and compare the two to determine a data dictionary of all the data used by all the programs, English glossary of all terms with indexed back to the software, an evolution of the terminology over the years. So they wanted the glossary to have a date for each of the terms and when the terms were coming into use and left and be replaced by some other synonym. They wanted structured diagrams of the programs, files, and data. And they wanted an analysis of the discrepancy between the programs and the documentation. Now, that is a lot of work. Now, to solve that problem, the task of translating English specifications directly to executable programs is very difficult. And you need an ontology that is specialized for the application. So in order to do that, the first thing that they did is take the much easier task of translating COBOL programs to conceptual graphs. COBOL programs are formally defined. Aaron wrote a formal grammar for COBOL. He used Prolog, by the way, which is an excellent language for writing parsers, translating the COBOL programs to conceptual graphs. And then those conceptual graphs provided the ontology and the background knowledge. So it's more than just ontology. They had a knowledge base of all the background knowledge represented in conceptual graphs. Now, in parsing English, they used the CGs from COBOL to resolve the ambiguities in the English. And they took the more complex structure of COBOL, even though it's more complex than English in its underlying semantics, it's more precise than English, so that you can have an exact parsing which is unambiguous. And then the conceptual graphs from COBOL were used to interpret the English. And then the CGs derived from COBOL provide a formal semantics for the informal English texts. And if you want to know what this looks like, the input, here's an example of the kind of language that they used in the slide 38. The input file that is used to create this piece of the billing interface for the general ledger is an extract from the 61-byte file that is created by the COBOL program bill CRUA and the billing history production run. The file is used instead of the history file for time efficiency. For this process, the following transaction codes are used: 32 loss on unbilled, 72 gain on uncollected, 85 loss on uncollected. All of this it's supposedly English, but this is a huge amount of complex English. And Aaron's parser was able to parse these sentences only because it first analyzed the COBOL. So the COBOL had all this information in it. So when it came up with a word like bill CRUA, that's not in your English dictionary, but it found that in some COBOL program. It was a name of a program. And in that program, it found all these transaction codes. And then it says, get B data, get B data to the client file. All of this is in the COBOL program. So it used the information from the COBOL program to interpret the English documentation. This could be documentation of any kind. It could be just an informal note from one person to another. It could be an email note. It could be a report. It could be a commentary. It can be code. It could be the commentary, then the comments inside the COBOL program. So this system not only analyzed the COBOL, it also analyzed the comments in the COBOL. And all of that was related to one another. And so here's the kind of things on the slide 39, shows how this information is linked together and how it's mapped to a conceptual graph in which it represents. Number 32 has a link to punctuation, which has a link to loss on unbilled. And then it goes on. Now, the job was finished in 8 weeks by Aaron Majumdar and Andre Leclerc. They did 4 weeks to customize their software to handle the design, ontology, and additional programming for the I/O formats, 3 weeks to adapt the software that used cognitive memory, and they ran this on 24 hours a day on an old-fashioned Pentium 3, and the matches with strong evidence, close semantic distances were assumed to be correct, and the weak matches, it would ring a bell, and then Aaron and Andre would go and check. They would either confirm it or correct it. And finally, after it did all that analysis, in 1 week, it produced a CD-ROM with the desired results. And the major consulting firm, this was done at the time when Anderson Consulting was changing its name to Concenture, and they had estimated that it would take 40 people 2 years to analyze the documentation and find all cross-references. But with the cognitive memory and the software that Aaron had developed, this task was completed in 15 person weeks. Now, you might ask, well, why didn't we make this more commercially available? Well, that's a long story, which I'm sure Aaron, and painful story, but Aaron can tell you more. But the point is that we went to various companies, and for one example was a company that was doing software reengineering. And we thought, this would be a fantastic help to for them to be able to do software reengineering with a system like this. Well, guess what they said? The first thing that the CEO said is, you mean you took a problem that would take 80 person years of billable time, and you reduce that to 15 person weeks? Get out of here. They don't want something that takes their job away. They want to get that 80 years of billable time, and they don't want to replace it with 15 person weeks. Well, that's just one example of the kind of things that we ran into in trying to make this commercial. But it was very important. It was an example of what can be done. But the point that is noticed that you had two senior programmers, Aaron Majumdar and Andre Leclerc, that had to spend 15 person weeks to run this software. The question is, can we do this today with people who have not had that training? In fact, people who were communicating with the computer only in their own native language, not in any kind of system like this. And that is the target. I believe that if this was done by two senior programmers 20 years ago, it should now be done by an ordinary human being sitting in a laptop and talking to a computer, either talking vocally or with typing in. That should be done today in ordinary language, and I believe it's possible. And one thing is that the thing discovered various discrepancies. One of the things that in doing the analysis, it discovered a diagram of relationships among the data types in the database. And there were the various relations. And the question is, which location determines the market? So one of the things is that the management wanted to relate the locations to the market. And the question is, here we have, according to the documentation, it said the business unit determines what the market area is, whether you're in the New York market, the Los Angeles market, or the Tokyo market. And according to the COBOL programs, it's the client headquarters that determine the location. So the client headquarters, for example, they might have a headquarters, and Deutsche Bank would have a headquarters in Germany, and their business unit was in New York. And so that according to the documentation, the location, the market location should be New York, but the computer was determining the client headquarters to be Germany. So this is a serious error, and for many years, management was making business decisions based on incorrect assumptions. And from another question is, here's another strange feature, another discrepancy. From the ontology used for interpreting English, every employee is a human being, and no human being is a computer. But when analyzing the COBOL programs, they discovered some employees are computers. And why did this happen? Well, the system discovered that. Some COBOL programmer made a quick patch. Two computers were used to assist the human consultants, but there was no provision to build for computer time. So therefore, the programmer named the computers Bob and Sally and assigned them employee IDs. So for more than 20 years, Bob and Sally were issued payroll checks. They never cashed them. And so the software discovered two computer employees. And these are the kinds of things that can be done. And the point is that the legacy reengineering task required two kinds of programs. They're precise reasoning, analyzing COBOL programs, and detecting discrepancies. It did indexing and cross-references, and creating an index of English terms and names of program, mapping English documents and files to the programs they mentioned. And the point is that the conceptual graphs that are derived from COBOL are precise, but the CGs derived from English are informal and unreliable. And it used the informal CGs are useful for cross-referencing between the English documents and the COBOL programs, but all the precise reasoning was performed on the conceptual graphs derived from COBOL or from English sentences that were translations that were corrected by the conceptual graphs from COBOL. So the interesting point is that COBOL and JCL, which are precise notations, were accepted as the gold standard, and the English was interpreted, the interpretation was assumed to be approximate, and it used the CGs derived from the formal languages to correct the CGs derived from English. Now, the point is that this is the kind of thing that can be done, that the sources here from natural language documents can come from, and the sources can be the natural language documents or structured data, and the query can be stated as an English sentence or a paragraph. And the idea is that you want to be able to have a dialogue in the application that Andre and Aaron and Andre implemented 20 years ago. They didn't have a dialogue, but they did have enough background information that Aaron and Andre could dig into the software and make the corrections. Today, what we want to do is have dialogues. So the tools, automated and semi-automated tools, should support a dialogue. Explanation requires more interaction than question answering. Both novices and experts should be able to carry on an